We are now in chapter 2. And in chapter 2, it's motion in 1 dimensions. So if I was to look at the overall view of this course, here's what I would like to see. The first thing here is that we want to connect chapter 1, which is the motion diagrams, to plotting position, velocity, and acceleration versus time. I cannot emphasize enough how important plotting is. It's one of the most important things that you're going to learn. Let me give you an example. This summer, I taught Physics 4C online. And last semester, I taught Engineering 15, which is circuit analysis for engineers. And the amount of graphing that we look at and have to interpret is quite a bit. So this is something that does not go away. Spend the time on plotting. And in Physics 4A, you're going to see that we have a lot of muscle in plotting. So this is the place to get a good start at it. And then the second part of this chapter is that we're going to look at kinematics, which is the mathematical study of motion. That means we now start setting up pictures with motion diagrams and graphs, and then we mathematically solve them using kinematics. So our lecture 2.1 is going to be plotting position and velocity versus time versus time for constant velocity. Then we're going to add changing velocity as well. Okay, so let's get started. So what we need to remember is that we started talking about average velocity. So what is average velocity? Well, velocity is a vector. So that means here, if I say the word average, that means I'm looking at the total displacement over time, and I look at the magnitude of this, and then we look at the direction. That's what we mean by the average velocity. So what this is telling me here is that this guy is going to tell us about the magnitude of the slope. But the slope has directions. And this is the direction of slope. We could have positive slope. So if I have a positive slope, we can interpret that as moving to the right. If we have a negative slope, that could be interpreted as moving to the left. So what we need to do here is that I really need to manipulate this equation for the speed or the average velocity. So in order to do that, I have to give you a very brief review in what do I mean by a linear line. So what I want to do here is that I want to look at a very brief review of a linear line. And so what we know about linear lines here is that the equation of a line is something that we know and love for a very long time, and it's equal to, of course, y equals to mx plus b, where we look at the slope is this m value, and this is what we call the rise over the run. And in this case, because we are plotting y versus x, the rise is going to be in the y direction and the run will be in the x direction. So in other words, if I have a line, okay, let's say that this is my line right here. I'm going to pick 2 points on this line. Let's say I pick a point here and I pick another point there. So what I can do here is that I can drop a point all the way down, and this will be T1, and I could drop this guy all the way down, and that will be T2. So in this case, I said time, didn't I? I don't want to say time, I want to say X. This tells me the delta X, which is, of course, the run. On the other hand, I have these other points, let's say, that look like this, and I could typically go all the way over here. And if I move these points all the way here to the side here, I could call this Y1, Y2, and this gives me the rise. So when I look at my triangle right here, this triangle has two details, right? It has two characteristics. It has the slope, which we just defined as the rise over the run, and we have a second piece of information that we have, which is B, which is the y-intercept. And in this case, we label this point B right here. Now, what I want to do here is that I want to take this linear line and I want to apply it to the average velocity. So I'm going to apply this technology to the average velocity. So when I look at the average velocity, we know that that is the speed here. And that speed is equal to delta x over delta t. So I'm just going to assume that delta x and delta t are positive. And this we define as the average speed. So now what I want to do here is that I want to rearrange this mathematically. So if I rearrange this, what I'm going to do here is that I'm going to solve for delta x. So if I solve for delta x, we know that delta x is going to be V average. It's not the way I want to write that. Times delta t. Or another way that we can write it here is that we can write out delta x. So there's two forms that are worth looking at. Or I can write this as x2 minus x1, which will then be V average times delta t. Now, here's some notation that happens. It's customary to do the following thing. And so what we do here is that we come in here and we say the following thing. We say here that delta t, which is T2 minus T1, what typically happens is we define T1 as the start of the stopwatch. Furthermore, we take this delta T2 and when we just defined it as T. So if I now rewrite this as a linear line equation, so if I now rewrite this as a linear line, here's what we get. We get that x2 is equal to x1 plus V average times t. And this is what we're interested in right here. This is the equation for constant velocity. So that's what I want to look at now. I want to look at constant velocity situations. So what we'll do here is that we're going to make the obvious choice here. And I think the obvious choice is that we should think about a stationary object. Okay, so let's break this up. We're going to have a stationary object, and then we're going to have moving objects. So we want to look at two situations. So here we go, case one. we want to look at what happens if I have a stationary object. So what do we mean by stationary? If I say the word stationary, of course it means it's not moving, right? It's not moving. And if it's not moving, we then say that the average speed of this object should be 0. But if I look at my linear line, this tells me now that the linear line equation shows me that this should be x2 equals to x1 plus 0 times t, which means that x1 and x2 should be the same. That is not a surprise. That's what we mean if it's stationary. It's going to be in the same position always. So what does this tells us here? So graphically, this means that the line has no slope. And therefore, no change in position. So if I graph this thing, what am I seeing here? So here's my position as a function of time, and here's my time. So when I'm looking at this thing, we can then see that we start off at some point, and we go to a second point. So at this point here, we know that I'm going to define this point right here at t1. But at t1, it starts off at x1. Over time, what actually happens? It moves from x1 to x2, which is also the same as x1, and this is at t2. So right away, what we're seeing here is that if I look at, there is no change in delta x because our slope here is equal to 0. So we see a flat line. So in summary, we could then say that no slope implies delta x is equal to 0, where an object does not move. In other words, it's at rest. I didn't have to tell you that. So then if I start to look at the velocity, what do I mean by the velocity? So then the velocity as a function of time is 0. Because we already said that average velocity was 0. So if I was to look at this same curve, and now I look at the velocity as a function of time, and then if I keep bringing my points all the way down to here, following from what we have up here, you could see here is that at this point, let's call this my red point, and over here, this is my green point, which we call that T2, and we call this T1. There is no velocity. It's flat. because v is equal to 0. Again, that is no surprise. It's not moving. Now, let's go to the second case. So our second case here, we now want to look at moving objects with constant velocity. So again, what do I mean by constant velocity? Constant velocity means I'm moving in the same direction and my speed does not change as a function of time. So if we look at this in the language of the line, we could say here is that if we have a moving object, I don't know, what about a moving car? Or we could have a person running. There must be a change in displacement. In other words, delta x has to change. And so look how we define the linear line. From the linear line, we said that delta x has to be v average delta t. So this immediately tells us, you know what, I said delta t. I should not do that. I should keep it as t because that's what we said. And so this implies here, so if I'm now moving, then v average is not 0, which then implies that delta x cannot be 0. So there has to be a change in position. So that's one way of looking at it from the line here. But if I look at it from the linear line as well, we can write this as x2 equals to x1 plus v average t. So this now tells me that we have a slope value that is not 0 anymore. And as a consequence, x1 and x2 cannot be the same. So let's graph this thing now. So graphically, how do we see this? So I'm going to imagine that I have two pieces to this graph. So the first thing that I'm going to do is that I'm going to go back to my original picture where I said this is x1 and this is t1. And this time I should have drawn a black dot. And then the other dot that I had here, and we said that this was x2 equal to x1, and that implies that delta x was equal to 0. So in this case, we said that this was t2. So our line is straight like this. If we have no change in delta x, which then immediately tells us that the average speed is 0 because there's no slope to this line. So in this case, this line right here tells us that this is the 0 velocity line. But now we know that there's a slope to this. And if there's a slope, that means I have to move to a different x2 value. So I'm going to move this up a little bit higher. And so what you're seeing here is that now, if I look all the way across here, I have definitely changed position now because I'm moving. So therefore, when I look at my line, you could see that I have this shaded area that differentiates between delta x equal to 0 versus delta x not equal to 0. So if I call this point 1 and I call this point 2, we're seeing here that now x2 is not the same as x1, which then tells us then delta x is not 0. And the cause of this is that the slope is not 0 anymore. There's a sloped line right here. So when I go and I look at this line right here, this is telling me that this is the non-zero velocity line. I am moving at a constant velocity because the slope is constant. Okay, let me make sure I have my chat open so I see it in case there's questions asked. So that's the upshot of this discussion here, and you can see here is that this is my delta x. That's what's really telling me here. So in summary, here's what we're saying here. So in summary, the cause of change in position, right, and displacement is the average velocity. And what I mean by that is that I'm saying delta x is equal to v average times t. You can see here that this right here, this is the cause. That's what causes the change. So now let's start associating pictures to try to show what am I actually seeing here. So let's see if I can get some good images for you here. So let's start off with some example here. And what I'm going to do here is that I'm going to consider two different cars moving with different speeds. But the same direction. So let's draw them this way. Let's say that I have this car, and I'll make this my red car. And so when I'm looking at this red car, this one is then going to be moving at a slower speed. And then I'm going to have a green car. And when I look at this car is going to be moving faster. So if I look at this thing, we could then say that in this case, this is slower. And because it's slower, that implies here is that its slope must be small. On the other hand, this is faster. So that tells me that its slope should be higher. So again, this is telling me that this has if it's slower, it has to have a smaller slope. This one has to have a larger slope. And as a consequence, then this means here that my change in displacement here for this car, which we could call 1, is going to be smaller, whereas the change in displacement for the second car, you know what? I should have probably put an equal sign because that's really what it is. It's an equal sign. This guy has a bigger change in slope. Maybe we should be talking about two values like this so that it's easier to identify what we're talking about when we start plotting these. That's what we mean by that. So now, here we go. So what we're seeing here is that the slope tells us how fast a car is moving. So what we'll say here then is that if you have a slower car, that means it has a less steep line. If I have a faster car, then I'm going to have a steeper line. So now if I start to look at this thing graphically, what does it look like? So graphically, this looks like this. So I'm going to have to draw a big graph to try to really squeeze it all in here. Let's see if that's big enough. Okay, so here we go. So if I look at the slower car, the red, then I need a smaller slope. So here I go. So I'm going to pick, let's say I pick a point here. And I'm going to call that my initial point x1 naught. And then this car, let's say, moves over to here. And this distance here, this is x1. So I want to try to avoid drawing too many lines. But what you're seeing here in this situation is that if I connect these two dots here, I'm going to have a line that looks something like this. So why do I know that this line has a less steep slope? Because I have to make a comparison. This, I'm going to say, is a small displacement. And this red line here, this is telling me that the slope is small because V1 average is small. On the other hand, I could pick two other points. Let's say that I pick this point right here, and I pick this point down here. Now, for my green car, you could see here that that's going to be my x2 value here. So when I look at this slope here, you could see right away that this is clearly a steeper curve. So when I look at the steepness, why is this thing steeper? Because when I look at the displacement, it is larger than the red displacement. So then this is telling me here that because this has a steeper slope, that means I have to have a higher average velocity too. And even though I did not label my axes, that is a bad thing. I would have taken points off myself for not labeling my axes. Not a good thing. So then if I look at the motion diagrams for this, these two have the same meaning. So if I look at this guy, I could say that I have dots like this. So if I look at my dots, that means that this speed clearly shows that I am moving slower to the right. And I see this because I look at this distance, right? I look at this distance between the dots and we come back and we say, yep, that was a small displacement. So therefore its average speed has to be slower. On the other hand, I could have intervals like this. Oops, wrong color. Let's say that I look at something like this here. So if I look at this, this is clearly a higher speed because I'm covering a larger area. So in this case, we see that we have this because the displacement covered between the dots is very large. The motion diagram and the graph mean the exact same things here. There's no difference between the two here. Okay, so now let's move on and let's sort of like summarize one more time and then let's get into the direction. So here's what we want to say here. So again, in summary, you could see that I am going to repeat the hell out of myself. If I can brainwash you into thinking these things naturally, then that's what I'm going to do. Part of teaching is repeating yourself. And I'm very good at repeating myself. So the slope, the magnitude of the slope tells us about the speed. And delta x. And we've seen here that this is what we find, that if delta x2 is greater than delta x1, that implies here is that the green car is faster than the red car. And we also said, in summary here, is that if I have a faster speed, then I have a steeper slope. On the other hand, if I have a slower speed, then I'm going to have a less steep slope. So that summarizes what we mean by the magnitude. Now, what we want to do here is we want to talk about the direction of motion. And when we start talking about the direction of motion, that means we must look at the sine of the slope. So then if I look at the slope, it's not a vector quantity, but it definitely feels like it, because when I look at the slope, I get two pieces of information. One, we get the so-called magnitude. And what we found for the magnitude, we were able to differentiate between fast versus slow. And we've already talked about that. We look at the steepness of the slope. Now what we're focusing on is that we're looking at the direction. So the direction of this thing, it's customary to say that if I have a positive slope, we typically say that that is the positive direction, or we can also say that it moves to the right. If I have a negative slope, it's either a minus sign, or we can actually state that it's going to the left. That's what we really want to think about right there. So now that we have this, what we can do here is that we want to look at two examples here. So as a nice example, I want to consider two different lines. So if I'm looking at this, what am I seeing here? So I have my graph, and what I'm looking at here is that I'm going to look at two different points. The first point is going to be this point 1. So 1 tells you that you are, if we look at this here, this means that we're looking at the origin of where we started measuring. So what I'm going to look at in this situation, I'm going to travel to some point 2, which I will label right here as 2. So if I look at this, you can clearly see that if I draw a slope between these 2 points, that guy is sloped positively. Okay, so this guy right here has a positive slope. On the other hand, I could have a different point. Let's say I have this guy right here, which is 3. And I'm realizing that I did not stretch this out enough. So let me slightly modify this. And how about if I go all the way down to here, and I'm going to pick some point, let's say right here, just an arbitrary point that I'm picking. And this is point 4. So you can see here is that if I look at the slope between these two, you can clearly see that the green line definitely has a steeper slope. And there's a couple of things that we should look at here. One thing here, look at that, the green line right here, what's it doing? It crosses the origin. That's not true of the red line. And another thing here, that this is past the origin, this point right here. And if I look at x3 here, you could see that this is farther from the origin. So it's telling us what these pictures are. And then right here, you can clearly see that this is a negative slope. So then if I start to look at this in terms of a motion diagram, let's say that, so if I look at this in terms of motion diagrams, we can clearly see that the magnitude of the slope for the red line has less steep line. So if I look at the red line, that tells us that this guy has a less steep slope. That tells me that this car is moving slowly. However, this is a positive slope. So therefore, this is moving to the right. But if I look at the green line, that's saying different things. This is a steeper slope. So that tells me that it's moving fast. However, the negative slope tells me that it's moving to the left. So now that we have those details, we can write this. So the first thing that I would look at here is that I would look at something like this here. I need to define an origin. Let's say that this guy right here is my origin right here. I might have to adjust my spacings. So I'm going to say that this line right here, this is my 0 point. And that is my origin. So what do I know about the red car, the red line? Well, the red line says that I'm going to define that this direction is positive or to the right, and this direction is negative or to the left. So now I have my coordinate system. So then if I look at my first dots here, what am I seeing here? Well, the red line is moving to the right, and it never goes back through the origin. So it's a little bit off the origin. So let's say it starts here, and it goes like this. So in this case, if I come back, I'm going to draw my arrows. And you see that this is moving constant velocity to the right. And it's going from point 1, and it's going to point 2 at constant velocity. But if I look at the green, you could see that the green at point 3 is farther away. So if I look at this thing, maybe I can then say that this point right here is going to be my green line where it starts. And if you look at this, that means that 3 point is farther away from the origin. So now if I start just, drawing in my vectors here, you could see here is that this guy is longer. And I'll stop right here. I don't think I need to draw another one. But what you're seeing here is that this is getting to point 4 here. So again, when I'm looking at these speeds here, you could see here that these guys are going to be slower. These guys are faster, but they're moving to the left. So there's how I connect the graph to the motion diagrams, they're really one and the same.